Let me start with some mock-up that I made, okay? So this is a box, right? And this is kind of like a mock-up of a neural unit, right? So we've been looking at these perceptron units, right? So think of these as a sort of a mechanical or an electrical box, right? So what happens in this neural unit is there are some input jacks on one end, all right? This is where some wires go in, right? These are what we call our inputs. So this is where our input would go in. And on the other side would be just an output jack from which another wire would probably stick out. And this is the output, all right? So that's a simple architecture of a neural unit, right? So what happens is that you put some inputs in, and you can think of it like putting some wires, and maybe the intensity of the current going in indicates the input, right? And same way, there's a wire coming out from this end, and the intensity of that current coming out tells you the output. And then maybe you can attach a light bulb to the end of it, and how much it lights up by tells you what is the output, right? So that's a simple sort of a structure. But what happens inside is when you open this box, right, what you get inside, so this is again the same schematic of the box, right, the inputs going in, output coming out. When you open this box, you see that inside there are a bunch of wires going in, and we have looked at it earlier, right? So what happens is that you have these inputs all going inside, and on each one of these leads, there is a weight attached to them, right? So this is a neural unit, and this is a neural unit number P. That's why you'll see a P everywhere. And the reason I do this is because later we'll have many units, so I want some way to index them. But with each input lead, there is a weight coming in, right? And what happens in this part is that this weight gets multiplied with these things, and then you get this output, right? And we are going to refer to that as net P. So net P mathematically can be written as WP transpose UP, right? So UP is a vector that denotes the input that is coming in. So together, all of these could be treated as a vector, and WP is a weight vector, and then the output net P is a scalar that is an inner product of these two vectors, right? And then there is another function here which gets applied on this net P, and then OP is essentially the output of that function. All right, so that's a general schematic of a neural unit. So far, in last two classes, we have seen two types of neural units, okay? We have seen one, what is called a perceptron unit, or a thresholded perceptron, thresholded unit, right? So in this unit, what happens is F is essentially a sort of a threshold function, okay? F is a threshold function. So the output of F, so F of net of P is +1 if net of P is greater than or equal to 0, and is equal to -1 if net of P is less than 0. Or it could be 0, one of them, right? So that's why we call it a threshold function, right? We have also looked at another unit, which is called a linear unit, or a unthresholded unit. All right. In this, F is basically identity, which means that the output of this kind of unit is just the net of P. All right. So that is the difference between these two units. Now the reason we looked at these two units was that if you want to use your perceptron, right, to do the prediction, to do the classification, which means it gets inputs and you have to find out if it's a positive or negative example, you always use a perceptron unit or a thresholded unit, because that gives you the positive negative, right? But when you have to train this perceptron, right? So when you buy this box from that machine learning store, right? Inside all these weights are maybe initialized to something. You need to train them. Maybe there are knobs over here which you need to set, right? So this is W1, W2, whatever, WD, and consider these as those turnable knobs, right? So you have to set these, right? So how do you set these? You set these by learning these weights from some training data, right? Now, when you have to learn those weights, we always use a linear unit or an unthresholded unit. And I'll tell you why, okay? So to do the prediction, we use the thresholded unit because that gives us the output that we desire. But when we are doing the training for learning those weights, W, we always use a linear unit. And there's a reason for that, right? So the reason is that it is easy to sort of compute the gradient for a unthresholded unit, all right? So when we are doing learning, right, we have seen that we want to do gradient descent. So to learn W of P, so let's say we are looking at this Pth neural unit. To learn this, what we do is we minimize error, right? Minimize, find the WP for which the error J of WP is minimal, right? So we're good. And so what will J of WP be? So for an unthresholded unit, we have seen that J of WP is nothing but half summation yi minus W transpose P, sorry, WP transpose xi square. Right? We've seen that before. Now this is a nice function. This is a smooth function. It's actually a parabola because it's quadratic in your input parameters, which means that it is easy to differentiate. And last class we saw how to compute the gradient of this function, right? Which is fine. So this is for a linear unit. So, but what if we use a thresholded unit or a perceptron unit? Right? In that case, our error function would change, right? So why would it change? Because the output of that perceptron is not this. Output of that is a +1 or -1, right? So think of that output. Let's call that output as this chi. So chi of I is equal to +1 if WP transpose xi is greater than equal to 0 and -1 otherwise. Right? So now if I compute my error, it would look like this. Chi I square, right? Now look at this. Now yi is your training labels, right? So these are always +1 or -1, right? These will also be +1 or -1. So when you subtract or add these can only take a few values, right? So this thing could either be, it could be 0 if both of them are same, or it could be 1, right? Because one of them, it could be 4, right? Because one of them could be +1, one of them -1, so +1 minus -1 is 2, and 2 squared is 4, right? Which means that this error function will no longer be smooth. It would look something like, let's say if you only had one weight, it would look like this, right? Is that clear? Right. Okay. Now, the problem with this is that it's not easy to differentiate this, right? Because this is not a smooth function, which means that the derivative at all of these flex points is undefined, right? So which means that it's hard to optimize this error function. And that is the reason, so hard to optimize. And that is the reason we use a linear unit, because that gives us a nice function. Yes, go ahead.
You said that you've been introduced to two types of units, which is a perceptron and a linear.
Right.
Which ones have you looked at that is linear? Is the gradient descent?
Yeah, so as I said, so the unit that we use for gradient descent is a linear unit, because there the output is just the W transpose X. So the linear unit, right? The output of this linear unit, OP, is actually W3 transpose X or UP. Whatever comes in from this aggregator is what is output. So that's why it's linear. The reason we say it is linear is because it just does a linear combination of your inputs, right? So when you W transpose X is just a linear combination. So for the training part, when we do the gradient descent, we use the linear unit. But when we are using it for the actual prediction, then we use the thresholded unit, because we do need +1 and -1 in the end. Any other questions? Yes, go ahead.
I began the exercise on the versions of the neural network.
Right.
And when I'm doing the function of net speed, I don't have like +1 and -1. I'm using the Sigmoid. It's not giving me +1 or -1.
Yeah, so the output might not be +1 or -1. You'll now have to apply the threshold, right? So if it is greater than 0, you call it +1. If it's less than 0, call it -1.
On the, if the net speed is greater than 0.
Yeah.
But function of net speed is going on net speed, so it doesn't.
No, eventually I think you have to do that. If it's the output, if it's the final output, and you do need some kind of decision, right? You want to know, is it one thing or another? So you will have to apply that threshold at the end. I'll talk about it a little more. All right. So with that, okay. So now comes the next point. The next point is that yes.
So at the beginning of the course, you made the assumption that the function that makes less error on the data is going to be the one that approximates the
Right.
next example. But now we are using two different functions. One for the training,
Right.
and another one for the prediction.
Right.
So we're going to have to do something.
Well, so that's a good question. The question is that earlier we talked about, this classifier. We want to learn those classifiers which give the best performance on the training data, right? One thing I want you to make to understand is that this function is not the classifier. This is just a function that goes inside the sigmoid unit. The classification function is actually this whole unit itself. So, which essentially is parameterized by these weights. So we want to find the weights that give you the best performance. The choice of the function inside might vary, and it would have an impact on what weights you learn. But the thing that we want to optimize on are these weights, not this function. This function is just a choice that we make before even starting anything. So it's kind of like a choice, before knowing anything about the training data, this is sort of a inductive bias that we make. That, okay, let's use this as a function. Now, that could be a terrible choice, but that's something that you wouldn't know until you sort of try it out and figure it out. So that's sort of a small distinction. Let me sort of move to neural networks, and then it will become a little more clear. All right? Okay. So one of the limitations of neural perceptrons is that they learn lines, right? To distinguish between two types of points, they learn a linear line or a plane. The another drawback of perceptrons is that they are useful to distinguish between two types of points, right? Positive and negative. What happens if you have many types of points and you're trying to build a classifier which can tell you it belongs to this category or class or this class or this class or that class? That's very similar to your programming assignment, where you get an input and you have to assign it to one of 10 classes, right? So each class corresponds to a digit. So is it 0 or 1 or 2 or 3 or 4? So of course perceptrons are limited in that sense, that they cannot give you that kind of multi-level output, right? So to address that issue, what the next type of classifiers we'll look at are called neural networks, and what they do is that they create a network of these perceptrons. So think of it like this. So when you go to your machine learning store, you can buy many of these units, right? And then you essentially arrange them. And then you create a network where you have one layer and then that goes to another layer. Everything is connected to everything else in consecutive layers and so on. And then more layers and more layers. And at the end, you'll have some output. So that's the structure of a neural network, right? And I'll tell you how it works, but that's a general schematic. And this would be sort of the output, and this is where the input would go in, and these are what we call hidden layers, all right? So the general idea is that if you want to get an output which helps you classify between 10 different classes, you should have 10 output nodes, so that each one of them gives you some output, and then you can choose the best one, right? So in our example, we can think of it like if you create these network of these boxes, at the output layer, you put a bulb at end of each one of these. Ooh, that's a bulb. But and then depending on the input, things happen in the middle, and at the end, whichever bulb lights up the brightest is your class, right? So that's kind of the idea, okay? And then we'll learn what goes inside. One of the drawbacks still is now the question to ask is when you go to your store is that what kind of unit should you buy, right? One option is to just buy the linear unit. You put all of these linear units and this propagates the current forward and gives you some output. But the problem is that if you use linear units, you would just be able to learn lines. So think of a simple example, 2D example. Let's say your data has two attributes, x1 and x2. And these are different types of points that you have. Let's do some triangles and some circles. All right. So you're trying to learn a classifier which can distinguish between these different types of points, right? So if you create a network which just has these linear units, what it will end up doing is it will learn a bunch of lines. Something like this, all right? Which is good enough, but in many cases you might want to learn, you might not want to restrict yourself to lines, right? Because in many cases, especially when you go to higher dimensions, just drawing lines might not be enough. So you might want to learn curves. So for example, you might want to learn curves like these. So these curves might do better on your training data, right? But of course, the linear unit would not help you do that, right? So now how do you convert this neural network so that it can learn these nonlinear boundaries? When I say nonlinear, essentially it's not a line, right? Nonlinear boundaries between many classes, right? We have seen that by converting a perceptron into a network, you can do multi-class, but to get these nonlinear behavior, what you do is you go and buy what is called a sigmoid unit. Okay? So a sigmoid unit is another type of unit. So we have seen linear unit, perceptron unit, and this is a sigmoid unit. The only difference between sigmoid unit and others is the function, the final function. And that comes to your question, is that, remember I was telling you about this structure of a neural unit. The function for the sigmoid unit is that f is a sigmoid function. A sigmoid function is essentially 1 over 1 plus e to the power minus net of p. So whatever is the input, it just does 1 over 1 plus e to the power minus of that. All right? So that is a sigmoid unit. Sigmoid unit is one in which the function, the final function, essentially takes your inputs and does a nonlinear transformation of that and produces that as an output. So you can see, because of this nonlinear behavior, now you introduce this notion of nonlinear discriminating lines. All right? Any questions so far? All right, so now let us try to understand how this works. So I talked about this, right? So essentially this is your multi-layer perceptron, and this is a very simple multi-layer neural network, which has an input layer, a hidden layer, and output layer. So every neural network will have an input layer and an output layer, because you need a layer to take the inputs and you need a layer to produce the output. In the middle, you can be flexible. So you can have one hidden layer, you can have 10 hidden layers, right? And in each hidden layer, you can put however many sigmoid units. It's up to you. All right? And each one of these units, so these green, blue, red, they are all similar. They're all sigmoid units. The only difference is at the output layer, it's slightly different. So at the output layer, because you do not really need, so the output would be scalar values all over the place. But eventually you need +1 for only one of them and -1 for all of them. So that is where you will apply a threshold. We will say, okay, if it is greater than 0, whichever is greater than 0, I'm going to call that 1 and everything else as -1, or whichever is the maximum. All right, any questions so far? Yes, go ahead.
If those few new variables
Yeah.
I'm not quite clicking on to, is the f the threshold or the?
F is a function that you apply to the W transpose X. So F could be a threshold, because that's also a function, right? So if it is a perceptron unit, then F is a threshold. If it is a linear unit, then F is just an identity. But if it is a sigmoid unit, then F is a sigmoid function. All right? And you can have many other nonlinear functions. So there's another popular one is what we call tan H, which just does a different manipulation of this input, right? So you can create any type of unit.
And so you're saying that the f function is applied to the W transpose F?
Yes, yes, yes. So,
What is that?
okay. So here, essentially what I did was I just introduced this variable. Net P is your W transpose X. I didn't want to write it over and over again, so that's why I just called it net P. So essentially, yeah, that's over here. So net P is the W transpose X, and then function F takes this value and produces an output. All right? Okay, so now let us see how the neural network works. All right, so before that, I also want to sort of introduce to you what is the effect of this function, okay? So we have actually seen these different functions. So this one is your threshold function, right? So whatever is the input, so net P is your input, right? So on the x-axis is net P, and what this does is it converts that into this kind of output, either -1 or +1, right? That's the effect of that. This is your linear unit. All it does is it just produces net output, net P outside. So that's just a same thing. And this is your sigmoid function. So what the sigmoid function does is that it converts your net P into this nonlinear output. All right? The reason, and you don't have to really understand it, but this is just to give you an intuition, is that, see, this is what you want, right? This is the type of output that you want. But we have seen that if you use this kind of output, it is hard to differentiate because it has this sort of a non-smooth property. This one kind of approximates this because its shape is very similar to this one, right? But it is still smooth. So that is why we use sigmoid, because it gives you kind of a close approximation of a 0-1 function, but it is smooth, so it's differentiable, which means it's easier to compute the gradient. All right? Okay. So now let's look at one. So actually you can create many types of neural networks. So depending on how do you set these hidden layers and how do you construct these wirings. So, so for example, you can say, I'm only going to connect only two wires can go out to each node and they get connected to something. So you can create your own architectures, right? So you can have different types of neural networks. Here we are going to look at one type of neural network, which is called a feed-forward neural network. And I'll tell you why it is feed-forward. But that's the essential structure of a feed-forward neural network is that there is an input layer, which essentially corresponds to the inputs. Then there is a hidden layer of sigmoid units, and there is a hidden output layer of sigmoid units, and then it produces the output, all right? The reason we call it a feed forward is because what happens is that you take your input data, right? So this is your bold X, this is your vector X, right? This is all the attributes of X. So we are assuming that X has 5 attributes, right? And let us assume that the 5th one is the bias unit, so the bias attribute. So 5 attributes, they all send all these X's go to each hidden node. So each hidden node gets all the input from here, right? Then inside it does its magic. It computes the W transpose X, and then it computes the net P and then the O of P, which is the sigmoid function on net P. And then it sends it out to all of your output units. And then the output unit also does the same thing. It takes the input and computes the W transpose X, or W transpose whatever the input is coming in, and then produces net of P, and then the sigmoid of P, sigmoid of net of P, and that becomes your O, right? So that's sort of the reason we call it feed forward, is because it sort of goes in this direction, forward direction. And at the end, you will get these 4 outputs, and whichever is the maximum, you will say that is the class. All right? So internally, the parameters of this whole neural network are bunch of weights. So remember, each sigmoid unit has a weight vector associated with it, right? So in this case, you have 1, 2, 3, 4, 5, 6 sigmoid units in the hidden layer. So there will be 6 weight vectors there, and 4 neural units, 4 sigmoid units at the output layer. So 4 weight vectors there. So total you will have 10 weight vectors. All right. So the forward step is pretty easy, right? And in your assignment, the first exercise, so I don't know how many of you have looked at the assignment, but in your assignment you have to essentially implement some function. So one of the function is called NN predict, neural network predict. So that function needs to implement the feed forward layer, right? So it goes from this end and goes all the way to this end, all right? And I'm going to describe it a little more. All right, again, so this is sort of the structure, right? So if you have D attributes on your data, then your input nodes will be D+1 because you have one bias node, right? And you also add a bias node on your hidden layer as well. So here, remember, there's one node here in the end which does not get any input because this is a bias node. So it always produces a 1 and sends it forward, right? The reason for having the bias node is the same. You need to introduce some kind of a bias if you do not have any input data, right? But so that's the structure. And then you have k output nodes. So if you have k classes that you want to distinguish between, then you have k output nodes. So in your assignment, your k would be 10. You have 10 output nodes, right? And now at each input node, you have a weight vector, all right? And I have tried to be as consistent in my notation as possible, but if you see some discrepancy, let me know. So J subscript will be used to index your hidden nodes, okay? So there are M, actually there should be M plus 1. M plus 1 hidden nodes. And for each hidden node, what you have is, well, actually you have M hidden nodes, right? Where you have weights, because the bias node doesn't really have weight, just sends out once. That's the job of that node. So you have M hidden nodes for which you have weight vectors, and you have K output nodes where you have weight vectors, right? So the hidden node weight vectors will have dimensionality D+1. So the reason being that the role of a hidden node So we are talking about multi-layer perceptrons, a feed-forward neural network. Right. So a hidden node, what does a hidden node do, right? So a hidden node, what it will do is that these are all your inputs, x1, x2, x3, xd plus 1, right? So one of the hidden nodes, and then you'll have multiple hidden nodes. But this hidden node, what it will do is, it will take these and it will combine them, do a linear combination, W transpose X of this bold of X, which is all of these in a vector, and then compute a sigmoid of that, right? So what you need here is a weight vector which has D+1 entries, right? Because you need to multiply them with all the entries coming in. So that is why we, at the hidden node, the W's, the WJ's, will all be D+1 weight vectors, right? And then the output node, what the output node does is, the output node will take the outputs of each one of these hidden nodes, right? So there are M+1 hidden nodes, including the bias node, and each one of them is sending some output. And this one combines them, does a W transpose of whatever. Now I'm not going to write x here because x was used for inputs, right? So these are the outputs of these nodes. Let's call them z. So z1 through zm plus 1, and this one just does a sort of a W transpose L of z. Z is a vector that contains all of these, and then does a sigmoid of that and sends it out. Right? So that's the O of L. So, which means that the weight vector that you need at each output node is a m plus 1 vector, has m plus 1 dimension, because it needs to take the m plus 1 input wires coming in. All right? So that's kind of the structure. All right. Any questions so far? All right. So this is easy. So the feed forward part is pretty easy. Okay. In fact, if you go through the assignment, you will see it's very well defined there. So the idea is that you start with your axis, right? So you assume that you already know all of these weights that you have at each node, right? So all you do is, in fact, let's try to do that. So this is the feed forward stage, the one in which we do the prediction, okay? So we have an input x, which is in RD plus 1, which means that it has D attributes and one bias node, or one bias attribute. Now what we do is, and we have, this is your hidden layer, and this is your output, okay? So let's say our D plus 1 is 4. Let's say there are 4 here, and let's not make it that big. 1, 2, 3, 4, 5. Let's say your m plus 1 is 5. That means there are 5 hidden nodes. And let's say your k is 3. That means you're trying to distinguish between 3 classes, right? And then these are all connected. So your x will essentially be, in this case, will be r of 5, right? Sorry, r of 4. Okay. So now what happens at each one of these nodes, right? So at each one of these, you will have a weight vector. So for this one, there will be a weight vector W1, W2, W3, W4. And we don't need a weight vector here because this is just a bias node. And to distinguish between sort of these two layers, because this will also be W1, W2, W3. But I'm going to call this as W1 raised to, I want to be consistent with the assignment so that you don't get confused. W1, we can call it W1. So these are like a superscript to tell you that these are the weights for the hidden layer, and then these are the weights for the output layer. All right? So in the first step, what we do is, for each L 1 through 4, which is here, what you do is you compute, first you compute net of L is equal to W L transpose your input x, right? Which is basically you're computing that net of L here, and then O of L, which is the output going out of this. Well, not L, we're using J here, sorry, J. J. So O of J will be, let's call it Z of J. Z of J is equal to sigmoid of WI1, WJ1 transpose X, which is essentially sigmoid of net of J. Right? So you compute this, right? So now what you do is, what you have after this step is that you have an output coming out of each one of these output nodes, right? Then you go to the next layer. For each L 1 through 3, right, which is over here, you compute net of L is again W transpose of, this is the second layer of L times the input that is coming to it, right? So there's an input coming from each one of them, and we are calling them Zj. So that's, so let's call this Z vector. This is input from each one of them. So you compute this, and then you compute O of L is sigmoid of this net of L. All right? And then that's it. At the end, you will have these outputs, and then you can say which one is the highest to say which class this is. So this is the feed-forward phase. Any questions so far? I'm sorry, what's that? Oh, you want this part? Okay. Yeah, it's the end. So all that's happening right now is that you're taking your input signal and you're passing it all the way to your output layer. So in general, if you are adventurous, you can have many more hidden layers, right? And the feed-forward phase stays the same. At each hidden layer, you take the inputs that are coming in, combine them to the sigmoid, pass it on, right? And at the end of the layer, you get this output. Okay? So if I give you a trained neural network in which all these weights are already defined, then constructing the prediction part is very easy, right? Implementing this is really easy, yeah? And that is one of the parts for the assignment. But the second, oh, go ahead.
Sorry. I just wanted to clarify. So when you do the transpose, you said it's against, so the one hidden is against each of the inputs. Is that what you're saying? So for each hidden node, you do the transpose against each input?
Yes, yes. Yeah, I didn't draw the wires here, but each hidden node is getting all the inputs, right? And the same way, each of your output layer is getting the inputs from all of them, and then all the other wires as well. So which is why this is actually a vector which gets combined with all of these. Other questions? Yes. I'm sorry, could you repeat? Yes. So the question is, will we have the same sigmoid function everywhere? Typically we do. There is no sort of reason to have the same sigmoid function. It just becomes more cumbersome to compute the gradient and everything. If it's the same sigmoid function, then computing the gradient, computing the feed forward, back forward is easy to implement. But in principle, you can have it different as well. Yes?
What about the bias? Do you add that to the final result?
So what happens with the bias is that, now it's easy to understand the bias here, right? This is just a value 1 that is going in. But at this layer, what happens is that you compute the output. So here you have computed Zj, right? Now, but Zj, you have computed Z1, Z2, Z3, and Z4 like this, right? But the Z5 will just be 1 because this is a bias unit. So you do not really compute it because, as I said, you do not even have a weight vector for the bias node because you do not need it. But you do need an output out, so you set that to 1. Oh yeah.
On gradients, the number of weights depends on the previous layer, not on the next one. Here, for example, it's got 3 weights because there are 3 but on gradients, we have like 5 weights because doesn't depend on the
well, in the feed forward, it only depends on the previous layer, output of the previous layer. Yeah.
But for example, the first unit of the hidden layer gonna have like gonna be multiplied by weight 1, weight 2, and weight 3.
Right. But no. So even here, and we can discuss this maybe later. I'm not entirely clear. Let's discuss it after the class, right? So yeah. But the main point is that it goes in the forward direction, which means the output at any layer only depends on what happens in the previous layer, and so on. So if you have many layers, it will only be in this direction. right? Now comes the next question is, how do you learn these weights, right? This side is beautiful. You have the weights, you do this forward prediction, you get the output. But how do you learn the weights, these W's, right? And that is what we're going to look at now, right? So the question is that if I give you a general structure, so you have to choose how many input layers you need, how many hidden layers you need and how many units per hidden layer you need. You do all of that, but after that, you need to estimate or learn these weights from some training data, okay? So how do you do that? So one way to do that, of course, is that we can try to minimize the error. Again, as we saw in perceptron, if we can somehow compute the error, the objective function, as a function of these weights, right? Then we can compute the gradient with respect to these weights, and then you can keep going, in the gradient descent mode, you can keep minimizing your error until you reach the minimum, right? So that is the basic idea, but it is not as easy as it sounds, right? The reason being that the error that you would define would not be directly related to your weight. So remember, in perceptron it was very easy, right? In perceptron, your error was your L of, or J, let's call it J. So J of W was half I equal to 1 through N Y I minus W transpose X of I square, right? So everything was here, and all you did was you differentiated, you computed the gradient of this with respect to your weights, and then you put it in your gradient descent, and then you got the answer, right? However, what we will see in neural networks is that you have to compute the J with respect to all of your weight vectors. So you'll have to compute this with respect to all of your hidden layer weights. In this case, we had 4, comma, all the output layer weights, right? And then compute the gradient with respect to these, right? So it's a little more challenging, okay? And now we are going to look at one algorithm that does that. Any questions before that? Yes, go ahead.
I'm sorry, back to the previous one. I just want to make sure that every DJ in the curve from the sigmoid curve.
Uh-huh.
So every DJ is a scalar from the W transpose X, right?
Right.
And then, but this scalar is every DJ in the curve. So it's on the curve or
Yeah, it's on the curve, right?
every DJ on.
Is on the curve, because that's out.
Actually, I will have my output will be on either side of the curve, and which determines as positive or negative, as true or false. Is it like that?
No, at the end what you do is that, so here, right, this is where you get your output. So O1, O2, O3, let's say your K was 3. Here all you do is you see which one is the highest.
In the curve.
Well, the curve was just to tell you that the output, this is the curve that I drew, right? So this is the sigmoid curve. Essentially what it says is that the output here, when you apply the sigmoid function, is between these two, it has this shape. So it will take one of these values, right? And then what you do is, then you do not really see if it's greater than 0 or not, because now you have multiple values, right? You have to choose one of them. Maybe more than one could be greater than 0. So you just take the one that is the highest, the one that gets activated the most. Yeah. Right. So we are going to look at it right now. So the question is, how do you minimize the error, right? So yes, so we are going to look at an algorithm that does that. It is going to give you the weight which guarantee minimum error. All right. But then you can go ahead and make your neural network more complicated. You can add more hidden nodes, or you can add more layers, right? But then you'll have to train it again. So there is no way to, from the training data, it is hard to know how many hidden layers or how many units do we need.
What's the pointer to increase the number of layers?
Well, so, well, that's kind of out of scope for our class, but I'll just discuss it. See, what happens is as you increase more layers, you are essentially trying to learn more complicated lines, curves, okay? So if you want to learn more and more complicated things, you would add more layers, right? But at some point, and that's a point of the second part of the assignment kind of talks about that, is that you do not really want too complicated layers. You want to keep it simple. So that's why typically you don't go beyond 1 or maybe 2 or 3. Nowadays with deep learning, they are trying to do more, and then there are some challenges there and everything. But in practice, even having one layer itself is good enough, right? See, neural networks are what they call universal function approximators, which means that if you have these x's, which are your inputs, and your output is a function of these. So it could be any nonlinear function. It takes all of these outputs and does all kind of mathematical manipulations on that and produces the output. You can learn a neural network which approximates that. So any function that you have can be approximated by some neural network. But in practice, our job is not to do the function approximation. Our job is to differentiate between these different types of digits or different types of points, and that's what we are going to do here. All right? Any more questions? All right. So let me quickly introduce this algorithm, and then we'll look at it later. Where is it? Not this. All right. So this algorithm that is used to learn these weights is called backpropagation. Okay, and we will see why it's called backpropagation. It comes from the fact that, you know, in the feed-forward part, you went this way. Now, when you are learning your weights, you go backwards, and that's why it's called backpropagation. And we are going to derive all the rules for that. So remember, the error function is still the same. Okay, so the error function for us looks very much like what it was for your learning. Here, just to keep it simple, I have assumed that we have only one training data. Okay, so which means that there is not another summation over here, but the error function looks like this. J is, for one training data, is half of YL minus OL whole square for all output classes. Now, this is a little different from the past, right? So because here in perceptrons, we had assumed that there are only 2 classes, but here you can have k classes, which means that you will have k outputs, right? Remember, if you remember your output layer in the feed forward, you will have k classes here, so k outputs. Our true label, we convert it into a vector, okay? So instead of having it, so because our true label essentially tells you which class it belongs to. So we convert it into 1 of k vector, which is, it is 1 for that entry, which is the true class, right? So let's say you have 10 classes, right? And your input example is digit number 7. So you will create a vector of all zeros or all minus ones, and you will make the 7th entry as +1, because that is the true class. That way, you can compute this error, okay? So YL is the target value, which is the true value that you have. It is 1 when k is true class and 0 or -1 otherwise. OL is the output that you get at each output layer, okay? So essentially what happens is that, if I go here, is that when I'm doing training, for a given input example, I already know what my true labels are. So this will be Y1, Y2, Y3. Only one of them will be 1, the one which is the true label. Everything else will be 0 or -1. It doesn't matter. So now you have a, sorry, oh, I'm out of time. Okay, so now you have an error function, all right? Now what we are going to do in the next class is we are going to compute the gradient of this error function with respect to all of our weight vectors. And then we are going to use that in the gradient descent algorithm to compute the optimal value for your weight